Good morning, everybody. I want to do a new recording of this MD Solids tutorial. The one I did through Zoom didn't seem to work very well, so we'll make this in a YouTube video and we'll see if that works. But at any rate, just Google MD Solids and it'll take you to a website. It says web.mst.edu, and when you click that, you'll get to this page. You'll want to go over here to the Download tab right there. So you download there. And here you can actually download the program. It's the latest version, 4.1. Right here is a code. And you can get it free for 30 days, I believe, without the code. But if you want to keep it for long term, then go to the file registration page and use that code. So keep track of that code, and then you can keep it for as long as you're in college or as long as you want. So let's actually go to the program and see what it looks like. All right, so here's the main page, and we're going to do a truss first. So just hit truss module right there, and it'll say create a new truss. And over here it'll ask you what truss do you want to look like, or what do you want the grid to look like. So I usually start with about 30 spaces in the horizontal, and about 20 spaces in the vertical. And when you do that, that creates a grid that's, those squares are pretty square in that way. So let's just create a truss. It starts with create, then you can create members, supports, and loads. So we'll do start with some members, and let's just do that. And here we're creating members, and we're gonna go this way over here like this. And just keep dragging and dropping until you get to whatever the truss you want it to look like. It will tell you if you try to create a truss that is an illegal truss, or in other words, it doesn't work. And it doesn't have to be symmetric or uniform, so I'm just going to create it like this. And here's going to be my truss looking like this. Now let's create some supports. Now it will try to generate all supports as rollers. If you put another one right there, but in order for it to compute properly, you have to make one of them into a pin. And so what I do is I just kind of drag it sideways, and it usually creates it into a pin and a roller. Now let's create some loads. I'm just going to pull down here and say start with where I want the load to start, and I'm going to go down and we'll call it 100 pounds. And let's go this way. We'll call that one 100, and we'll call this one 100. All right, now you should know enough about truss analysis now. You should be able to predict some of these truss member forces. For example, this one is pulling down at the joint with 100. These are collinear members, such that you should expect that this one right here will be 100 in tension. This one is also sitting on a support. So whatever that support is pushing straight up. So whatever the support value is, or the reaction is, then you should expect this one to be in tension, or sorry, in compression, pushing down. And then this one right here, you should expect to be a zero force member. So we're just going to hit compute, and indeed. Now if the fonts are a little too big, you can go up here to File and change font, and I'm just going to make the fonts about 12 point, makes them a little easier to see. It's a little bit small. Let's go a little bit bigger, maybe about 16. On my computer, I got a high resolution monitor here. But all right, so basically you can see what happened here. I got a zero force member. This one's 100 in tension. This one's going to be whatever that reaction was, 1661. This one's going to be in compression. Now let's create another load. Let's draw a load right there. Now when you do that, it has to recompute everything. Again, but how have I changed this thing? Well, clearly I've added a load here. It's going to change those reactions somewhat. Is this one still going to be 100 in tension? And I think so. This one will still be whatever that support is in compression. How about this one? This was a zero force member. Has that one changed? Well, let's compute and find out. And indeed it does not. By virtue of this joint, we know that this one's going to be 0, because the only way for this one to not be 0 would be if there was a load going up or a load pulling down. or some angle and that sort of thing. Anyway, so that's kind of the way you do truss analysis, and I'll give you some homework problems where you have to create this and enter those into mastering. All right, let's go back, and now let's do a determinant beam. Now here you can create fixed support beams, cantilever beams, or you can do simply supported beams. So we're just going to do this one first. We're going to make this in units of feet and make it 10 feet long. And we're going to take the left support at 0 and the right support at 7. And then we enter that and we'll see a picture of the beam over here. And that's what the beam looks like. Now let's create some loads. Let's take a downward force load. We're going to put it at 3 feet. And we're going to make the magnitude 100. And we'll see what happens. And you can kind of see what happens with the shear moment diagrams. It instantly creates shear moment diagrams where there's a reaction over here. It goes up and then it goes down 100. So it goes to there between reactions or applied forces. Then it is even or level. Then it goes up here and there's nothing going on out there. Obviously, the moment diagram has a peak moment right where the shear crosses the x-axis. Well, let's now create a distributed force and see what happens. So here's a uniformly distributed force. I'm going to start this at 5 and end it at 10, so at the end of the beam. And I'm going to make the magnitude 40 pounds per foot. And let's just see what it looks like. Whoa, what's happening here? Well, here I have the shear diagram, and here you can see the moment diagram. Again, where the shear crosses the x-axis, you should see peak moments. And indeed, where our peak moment is right down there. It is negative 180, where this force crosses the x-axis right there. You can go back and modify things if you want, but this kind of gives you a way of drawing a picture of a beam and instantly computing the shear moment diagrams. All right, now we're going to go back out of here, and I'm going to show you one more module, and that is section properties. And this is where the little contest is all about. And you can create section properties of different kinds of beams, and we're looking at the cross-section beam. So I'm going to create a flanged beam, a general flanged beam. And here's a picture of an I-beam, a general flange beam, and you can put the dimensions in. So I'm just going to say that I want it 1 inch. Oh, and you can change it from millimeters to inches. I usually, unless for some reason, well, whatever. We're going to make this one into inches. So I'm going to say it's 1 inch thick here, and 1 inch thick here, 1 inch thick here. Now let's make this beam 5 inches wide on the top. 10 inches tall, that's the flange length, and then we'll make it 8 inches wide on the bottom. And when you compute that, it redraws the beam in kind of the proportions that you made it, and then you get over here and you can see some of the properties of the section. I used 23 square inches of material. I was able to compute the neutral axis, the z-axis, it's down here, from the bottom to the z-axis is 4.5. From the top to the z-axis is 7.5. Now z meaning the neutral axis. And for purposes of chapter 10, we're going to compute the moment of inertia about that neutral axis. So here's kind of the demo of how you do this, and your challenge will be to create the beam using the criteria given in the contest to create the moment of inertia, the maximum moment of inertia given those criteria. So anyway, that's the demo, and I hope that makes sense to you, and I'll quit now.